let's get started. What we're doing today, if you didn't get an email, because of UO's wonderful email system the last few days. I don't know how yours is going to behave, but I can hardly read mine. We're going to I'll take review questions for as long as you have them. So there's an exam on Thursday, and it'll be roughly the same form as the last one. I don't know if there'll be choice or not. It depends on how hard I think it is. But it'll be about the same number of questions, same style, and all that sort of thing. So, yeah. And so if you have questions, you want me to review for it, great. From my notes here, it starts with policy effectiveness. It goes through the material on last Tuesday, a week ago. That seems fair enough, or a week and a half. Which was on the facts about growth. We didn't quite finish everything in that chapter. We roughly got through a lot of it. And so I tried to put up some practice questions on the things we haven't had homework on. You can be pretty sure there'll be questions that are like the homework questions. So if you copied your homework from your friend, you probably won't actually learn what it means. That's one way to sort of insulate against that. And it'll just be straightforward stuff. If you know the material, you'll do fine. If you don't know the material, then that's what I want to know. And so, I'm not going to try to trick you, anything like that. And maybe the last one you saw that. So, what are your questions?
Is there anything specifically you want to see when
So I want you to know, yeah, I make sure I use the same notation as the book. So what we did to derive the Phillips curve is we took a very, very specific case of the one second, I want to make sure I use the same notation. So we started off with the equilibrium. So we have this model of a labor market, essentially. The price setting equation and the wage setting equation. It gives us this P over 1 plus M and PE F and C. And so this point right here is where P equals, say, 1 plus M PE F of U and C. So you start with this equation, do it algebraically. If you want to put the 1 plus M over here and then multiply, that's fine. I skipped a step. But that's nothing more than the equilibrium in this market. Then what we did is we took a specific case and let, for illustration, F of U and Z be, what primers do we use? 1 minus alpha U plus Z. We just took a specific linear case. And we said, okay, well then P equals 1 plus M PE times 1 minus alpha U plus Z. Then we said you can approximate this by inflation equals expected inflation plus M minus Z, that's plus Z, made that mistake the first time, minus alpha U. And then that's the Phillips curve. And so it's just that step. You just start with the labor market equilibrium, put in a specific F of U and Z, and then say, okay, this has to be the Phillips curve. And what it gives me, now the sort of wave my hands part is here to here. You just kind of have, you can't really derive that unless you know how to take approximations. It relies upon some log approximations. Just wave your hand and say, this is it. And then what you get And there's a relationship between inflation and unemployment. This one's linear, looks like this. This intercept will be IE plus M plus Z, and the slope is minus alpha. That's the slope parameter, that's the intercept for that particular line. And so algebraically, that is how I would do it. So that was the review questions from 8 and 10. Problem 1.
So when you say explain why and how the bell curve shows the changes in pi, E, and Z, is it just those are the y-intercepts and so it goes up and down?
Yeah, so there's a typo in my question, I see.
Is there monopoly poser?
Which one?
Monopoly posers?
That's it partly, that's kind of funny. But it's actually, that PE should be inflation. That should have been it. Should be this, not PE. I should fix that. This is, what is that, question number 3? I'm fixing it right now. Poser. Anyway, I didn't ask a question, then that's all. Really? New material I'm on?
There could be a question on vocabulary stuff again, or that's really just chapter 1 stuff?
There could be definitions of things, simple sorts of things. We talked a little bit about unemployment and other sorts of things that sort of lend themselves to those kinds of questions. There could be, but, yeah. Go ahead.
Well, that's a question, right? You need to get-
Do it now. Inflationary expectations. So what I'm looking for there is that you know filter looks like this, and it's based upon particular expectation. And when that expectation, is correct, you're at the natural rate of unemployment. And so there's this medium run Phillips curve where expectations are correct. And there's this other Phillips curve we move along when expectations are incorrect. Then when you start shifting the thing, okay, review questions are fixed, you don't have to worry about the error. Errors are fixed. Then if we say have inflationary expectations increase to pi 1, it'll shift out. But you also want to know that this point here has to be pi 1. So for instance, if we were to move up to here and try to stay there permanently, we probably couldn't, because expectations would change and we'd shift to this point. So I'm mainly looking for that kind of an explanation on that particular problem. Yeah.
So you say you can't move back to
Sure. You could lower inflation, and if inflation expectations fell, you go that way. If inflation expectations go up, you go that way. So it shifts in both directions. Mechanically, it's just because its intercept is pi e. But there's a little more to it than that. You just want to recognize that when these expectations shift, you shift along this medium run Phillips curve in this particular way. And so I just...
up or down.
What's that?
Up or down, depending on the expectation.
Right, right. When expectations go up, it shifts out. When expectations go down, it shifts in. Now, whether you have to go A, B, C, or A to C depends upon credibility. And that's, I don't think I really asked about that, but that's part of that story that I'm looking for in problem 4, and even more so about the costs of problem 7, about the costs of disinflation. When it's costly, when it isn't costly, and that's for problem 7 on there, depends critically on credibility. Say you're at this point here, and you want to lower the inflation rate from pi 1 to pi 0, from 10 to 5%. So you announce to people, hey, tomorrow I'm going to cut the money growth rate from 10% to 5%. Inflation is going to fall. If they believe you, you can shift almost directly to this point. You won't have to pay much of an unemployment cost. Because you say it, they believe you, and the curve shifts. But if they don't believe you, what has to happen is you're going to move along this Phillips curve here from A to B, because they're saying, okay, you say, I'm going to lower the inflation rate. They say, we don't believe you. So they keep their expectations where they were. Then you have to actually do it. And if you keep it here long enough, they're going to say, oh, okay, yeah, you really were serious this time. Unlike all those times in the past when the Libelists said you're going to lower the inflation rate, it really didn't come down. This time you must mean it. So then the expectations would shift in and you went to this point. But there would be a much more costly adjustment in that case. So problem 7 is really about that fight between Lucas and others, Chicago school types, who thought that they had enough credibility and could just announce that it would, I wonder if I turned that camera on. I don't remember turning it on. And announce that it would move it, which you would go from just A to C without paying much of an unemployment cost. And others have said, no, it's going to be a substantial cost because the Fed doesn't have credibility and you're going to have to show it. And it turns out that latter group are the ones who actually won the day. Turns out the Fed really didn't seem to have much credibility and there was a huge unemployment issue. Oh, it's fine. Yeah. So one thing I really want you to be able to do is sort of use this model to tell those stories. First, they thought there was a permanent trade-off in the 60s. They tried to get to this point. Phillips curve started shifting. They increased inflation even more. Phillips curve shifted again. They got stuck in this high inflation, high unemployment equilibrium. And to get out of it, they had to pay a huge unemployment cost initially. And then as they reestablished their credibility, they were able to bring down the inflation rate with a much smaller cost in the late 80s and the 90s. We didn't see a big unemployment surge, even though inflation kept coming down to around 2 to 3%. But that initial period where they didn't have credibility was quite costly. And so, be able to tell the story how they got into that box when they had high inflation and high unemployment, and then what they had to do to get out of it, and why it was so costly, and about this debate. That's really problems. Problem 7, and problem 4 and 7 are those 2 problems.
Can you go over like monetary policy and fiscal policy for I going up? And also LI, the chart, monetary policy.
Okay, so this is about policy effectiveness graphically, intuitively. I didn't do these mathematically. You can write down the formula if you want. Probably don't. So let's do I of I. So the question is, are monetary and fiscal policy more or less effective when the responsiveness of investment to the interest rate goes up? So always read this as the responsiveness of this to that. How much this responds to a change in that. Change in this due to a change in that, all else equal. That's what those things mean. Now what we should register. So if the responsiveness of investment to the interest rate goes up, or the absolute value of that parameter goes up, is monetary policy and fiscal policy more or less effective? So these are problems right off your homework. This is not a section that's in your book. Threw this in as a bonus for you. Now what we know is that when I of I goes up in absolute value, the IS curve gets flatter. You can just take that as given. So what we have are 2 different IS curves. There's this one and there's that one. These are the solutions I posted yesterday, for example. And then there's an LM. Let's do monetary policy first, because it's pretty easy to say. So there's Y0. I'm not really caring about the interest rate too much here, so I won't keep track of it. This is all that I output. So we increase the money supply. LM, M1 over P. This is the one for a more responsive investment to the interest rate. So what we see is that when the curve is steep, you get there. When it's flatter, you get to that point. So this is the more responsive. So monetary policy is more effective when investment responds more to the interest rate. And the intuition is just trivial here. When M goes up, money supply is greater than money demand. That causes the interest rate to fall, investment to go up, and output to go up. This is where the responsiveness. For a given M, change in M is the same for both times. For a given change in M, if we have a bigger increase in I, it's more responsive, we get a bigger change in Y. So it's more effective. So up to here, everything's the same, and if I responds more, you get a bigger change in output. Fiscal policy is a little more complicated to do because we have to shift both IS curves. But the startup is the same. You have a steep IS curve, flat IS curve. That's where you've got a more responsive investment to the interest rate, and an LM curve. you have to do in this case is to shift the point of intersection of those two curves. So here's where we're starting. We need to shift this point of intersection horizontally, not vertically, but horizontally in this case. So we increase fiscal policy, we increase government spending, and both IS curves shift horizontally by the same amount. So the flat one shifts like that, and the equilibrium will be there. And the steep one shifts like that. So the equilibrium will be there. So you either get to this point or this point. This is the flat curve this time. This is more responsive. So now this time we see that it becomes less effective. Fiscal policy becomes less effective as the responsiveness goes up. That's just the opposite of the other case. Monetary policy is more responsive. The reason here is because you get less crowding out. This was the monetary one here. When government spending goes up or taxes go down, that's going to cause output to go up. That causes money demand to go up. Money demand greater than money supply causes the interest rate to go up. This is the crowding out. Investment to go down and output to go down. This is an offset to that increase in output. So again, here is the responsiveness, this is crowding out. You get more crowding out when you have a more responsive investment to the interest rate. And the more crowding out you have, the less effective policy is going to be, because your offset is even bigger. This here is, you move from here to here, that's this part. Then you get crowding out, and you get more crowding out when the curve is flat. So you can think of this A, B, C, and C prime. So this is A to B here. And this is B to C, or B to C prime, depending upon which case you have. So we got more crowding out with that flatter curve that is more responsive. Interest rates are driven up by government spending. What's going on is that this is deficit spending. The government's got to borrow the money, so they're competing for funds. That drives interest rates up. When interest rates go up, investment falls. And the more investment falls, the more crowding out you have, the less effective policy will be. Right now, we think crowding out's almost zero. It's for a different reason, though. There's so much money around that there's a bunch of extra money piled up in banks and corporations. There's huge amounts of excess reserves. So you can borrow more money without putting upward pressure on the interest rate right now. At normal times, you get crowding out. Yes?
Where does B fit back in?
What or what now?
B, looks like B, where does it fit in?
Here's B, A to B.
You also want as far as the intuition flow.
That's output going up from A to B. Output goes up from A to B. Then you get crowding out to either C prime or to C, depending upon which curve. So up to this point, they both shift the same. It's a horizontal shift. This is actually the multiplier, 1 over 1 minus the MPC. That's the horizontal shift. And then you get the crowding out. What's that? Yes, it's less effective when you get more responsive, yes.
Yeah, I'm quite confused because the steeper IS curves seems to move the output farther.
Right. And that's smaller ILI.
Oh, it's smaller. Okay, okay.
So the flat one is the more responsive. And it shifts to there. The bigger I volume is, the flatter the ISR is.
I was kind of confused with the other one.
The slope is 1 minus c of y minus t over I plus y. So the bigger that is, the flatter the curve gets. Yeah. So the flatter curve is less effective, and the flatter curve is more responsive. Bigger I volume. So there's two mores here. Yeah, different.
And the Siever II represents more of a recession scenario, right?
So that's where I was going to head next, yes. Because we think investment is fairly unresponsive in recessions because there's no reason to invest in it. You've got all this excess capacity, why are you going to invest more? Just because the interest rate falls. So right now, there's actually, so Keynes, this is, I didn't really talk about this. So Keynes said there's many a slip twixt cup and lip for monetary policy. And what he meant was for monetary policy, there's a lot that can go wrong here. So if you're going to use monetary policy in a recession, the first thing that has to happen is you have to be able to lower interest rates. Well, if you're at the zero bound, this breaks down. Right now, we can't lower interest rates anymore. So you can't even get this far. Even if you could lower the interest rate, this probably wouldn't respond. And so getting output to go up with monetary policy requires a lot of things to go right. You've got to be able to lower interest rates, and the fall of the interest rate has to generate new spending. Those are all incentive effects. You're sort of, leading the horse to the water, hoping that here you're force feeding this stupid horse. Government spending is part of output. And so when you increase government spending, output goes up. It just happens directly. Now you've got this offset. We think it's relatively small in a recession, but government spending operates much more directly. There's not a lot that's going to go wrong here. You can have a big offset through crowding out, but it's got this direct impact on output, and so it probably works better in a recession for that reason. So it's just another way of sort of saying the same thing. All the things that can go wrong with monetary policy do go wrong in a recession. Near full employment, the thing that can go wrong with government spending, lots and lots of crowding out, does happen. So near full employment, this is a better tool for affecting output. In a recession, according to this model, this is the better. L of I, the analysis is exactly the same, except the LM curve rather than the IS curve is what has different slopes. So let's try that one next. If you were to do the math, that's the answer you get for fiscal policy. Let's do L of I. So the very first thing you have to know to be able to do this problem is, okay, L of I goes up. What happens to the slope of the LM curve? If you can't get that far, you can't really do the problem. There's two answers, and that's probably not it. Yeah, it gets flat. Yes, it gets flat. BI is minus LI or L of Y or L of I. Yeah. So when L of I goes up, the LM curve gets flat. Everyone agree? Did you remember? That's what I remember. So let's do fiscal policy first, because it'll be easy. So now we're going to have two LM curves. That one and this one. And this is where we have a more responsive money demand to the interest rate. That is, L of I gets bigger in absolute value. So now we're doing the L of I parameter. L is money demand, so it's responsive money demand to the interest rate. So that gets bigger. We think this LL curve is almost horizontal in recession, so keep that in mind. That's the liquidity trap. It comes about because money and bonds become perfect substitutes. But we won't get too much into that. Anyway, so you have an IS curve, an initial level of output. We let government spending go up or taxes go down. The IS curve shifts out. And what we see is that when we have a more responsive money demand to the interest rate, flat one, it's more effective. So this is just a different link. So government spending goes up, that causes output to go up, that causes money demand to go up, drives interest rate up, drives investment down, which drives output down. This is the crowding out part. Where this matters is right here. So it must be that crowding out is less in this case, because it's working on this crowding out part. It's this link right here. It's a relationship between money demand and the interest rate. See, if money demand is really responsive, so what happens here is money demand is greater than money supply. So we need to change the interest rate to make these equal again, right? If it's really responsive, we only need a tiny interest rate change to get an equilibrium again. We've got a really responsive money demand, a small increase in interest rates is going to give us a big change in money demand. So when it's really responsive, like the flat case, we only need a tiny increase in the interest rate to restore equilibrium. That means if this is small, this is small. We get small crowding out. So government spending goes up. That drives output up. People need more money because they're buying more stuff. So money demand goes up. Money supply hasn't changed. We need to raise the interest rate to bring money demand back down. If it's really responsive, we only have to raise the interest rate a little bit. The money demand will come down a lot. If it's not very responsive, like here, we have to increase the interest rate a whole bunch to bring money demand down. If we have to increase the interest rate by a whole bunch, we're going to get a lot of crowding out and it'll be less effective. So that's what the intuition for this one's a little trickier. It's how much does the interest rate have to go up to make these equal again? If it's responsive, not very much. If it's unresponsive, a whole lot. And that tells you how much crowding out there's going to be, either a little bit or a lot.
Your fiscal policy.
It's more effective when you've got a more responsive money demand, because you again only require a small interest rate increase. You get less crowding out in that case, but you don't need to change interest rates very much. Now, monetary policy is going to be different. So again, steep LM, flatter LM. This is the more responsive case. If it's flatter, an IS curve, that. So this time we have to shift both LM curves. And again, we want to shift them horizontally. And so take this point, which is our initial point, shift it horizontally, and see what happens in the two cases. The flatter curve will shift like that, and we'll end up here. Steeper curve will shift. It's just a horizontal, like that, and we'll end up there. This was the bigger LOI, the more responsive flat one. So it's just the opposite here. For monetary policy, when you have a more responsive, less responsive money demand and the interest rate, you get a bigger impact. Again, when M goes up, money supply is greater than money demand. That causes the interest rate to fall, the investment to go up, and output to go up. It's all about here. How much does the interest rate have to fall to make those equal again? So here what has to happen is the money supply went up. So you have to lower the interest rate in order to bring money demand equal to money supply again. So I has to fall. If it's really responsive, that's the flat case, I doesn't have to fall very much, so you don't get much of an increase in output. If it's unresponsive, I has to fall a whole lot, so you get a big change in output. So when it's unresponsive, you need a big change in I to clear the money market, and that big change in I generates a big change in Y. See that? So if the LM curve were completely flat, like in a liquidity trap, what if the LM curve looks like this? What's monetary policy do? You shift it horizontally, you stretch it out that way. It doesn't change anything. So if the LM curve were completely flat, that's L of I equals infinity. You get that. That happens when money and bonds are perfect substitutes. That happens at the zero bound. If interest rates are zero, bonds don't pay any interest. They're just like non-interest bearing stuff. And so bonds and money become substitutes, and you get that flat L curve in that case. So in recessions, we think this is what happens. Fiscal policy is effective, very effective, more than if it had a slope. Monetary policy is completely ineffective.
Pretty much making what I showed you is a curve with the bigger LOI and the smaller output.
Yes, and to explain why. And then to recognize that the big LOI case is the recession case. So that you get exactly the same result here. Fiscal policy is more effective in a recession, monetary policy is more effective for forward. The implications are identical to what we just did in terms of the business cycle. So L of I going up and I going up give you exactly the same result in terms of the relative effectiveness of monetary and fiscal policy. When these go up, it's flatter. Monetary policy is more effective and fiscal policy is less effective in both cases. So they work exactly the same. When they go down, as in a recession, fiscal policy gets more effective, monetary policy becomes less. So when these go up, monetary policy is more effective, and fiscal is less. And that happens as you move towards full employment. And vice versa. Near full employment. In the opposite case. What else? I think that's pretty much all the policy effectiveness stuff we did. You do those right? Copies? It's fine.
On number 11, it says, use the structure function, the assumption constant returns from scale to show that growth depends upon K over N and hence upon capital.
Yeah.
So it says upon capital accumulation and technological progress. And I was just wondering about the technological progress part.
Okay. So you have Y is some function of capital and labor, number of workers. When it's constant returns to scale, you can divide one of those terms by a constant. So I can say that then it must be under CRS. Constant returns to scale, it must be that Y over N equals F of K over N and 1. And so capital accumulation is just K going up. So if K goes up with N constant, we'll get a growth in output per person. The capital accumulation part is just that K over N. Technological progress is embedded in the function. So if I had like a Cobb Douglas, Y equals A, K to the alpha, L to the 1 minus alpha, technological progress would be this A term. It would then be that Y over N equals A times K over N to the alpha times 1 to the 1 minus alpha. So if I were to divide through, I could show that were true. So growth in this depends upon two things. It depends upon capital accumulation relative to labor, and it depends upon technological progress. With the same K and N, if A gets bigger, we have more output with the same inputs. And so we're defining technological progress in terms of productivity. We're getting more and more productive because we're getting better and better with our technology. We're getting more and more out of the same inputs to the production process. And so it's either A going up with this fix that causes Y over N to go up, that's technological progress, or it's accumulation of capital relative to labor that causes growth. This is the standard of living. So we talked about this is a good way to measure the standard of living. So we're asking what makes the standard of living go up over time? And the answer from this model is there's two things that cause it. This and this. So later in the next chapter, we're going to fix this and this, and just look at K and we're just going to look at capital accumulation.
Would that be the
A is just a parameter, a number. And it's, you can think of this as A of T. And A of T is capturing the technology. Because as A gets bigger and bigger and bigger, with the same K and the same N, we'll have more and more output. And so technological progress is making this more and more productive. Same K, same N, more, bigger Y over N. So that's what we mean by technological progress. Well, and not, well, I should be talking about it in the next. Yes? What's that in parentheses? That's the K. Comma 1. I just divide through by n. And you can do that when you have constant returns to scale. If I divide this by n, I get minus 1. So I get a minus alpha, so I can just be in k over n. So what we'll do soon is connect K to savings. Savings equals investment, investment's the change in capital. And so the growth of the capital stock, capital accumulation, will depend upon depreciation, how fast capital deteriorates, and investment, how fast we're adding to it. Adding to it faster than it's depreciating, capital will grow over time, so if savings is high enough, we'll get enough investment, have capital grow and have the standard of living grow. If savings is too low relative to depreciation, the capital stock can actually decline over time, and your standard of living will fall. So then you can ask, what's the optimal savings rate to maximize consumption? So we're going to start looking at these, with this growth model, how growth relates to savings and things like that. That's what I'm ready to do when you run out of questions.
We drive that AD and AS curve from the.
Sure. On the graphic line.
Yeah.
Drive AD and AS graphically. Let's do AD first because it's probably a little more straightforward. So AD is ISLM put together. So to get the AD curve, we take the ISLM model and ask it a question. How are P and Y related? So hello, ISLM model. If I change P, how does Y change? That gives me the aggregate demand curve. So I just write down the ISLM M over P0 model. So what I know is that at P0, I get Y0 as my output. And then I ask the ISLM model, hey, if I change the price, how does output change? And it tells me. So I say, okay, let's lower the price to P1. I could have raised the price, makes no difference. I'm just asking, how are P and Y related? So, hello, ISLM curve. If I lower P, what happens? I say, oh, well, M over P goes up, but P goes down. So it must be that the LM curve shifts out M over P1, because this is now bigger. So at the lower price, output goes up. So it must be that the demand curve has a negative slope. And that's it. Sure. When M goes up, money supply is greater than money demand, interest rate falls, output goes up. Well, investment goes up, output goes up. Oops, sorry. When P goes down, M over P goes up. So money supply is greater than money demand. Blah, blah. So there's a negative relationship between price and output. Trying to think it was worthwhile writing the algebra, but I don't think it was enough for this one. And whether P is what, Y, L, I. For the AS curve, we need to start with the labor market and the production function and so on, and see how, so for the aggregate supply curve, you can start with the wage and price segment equations. So you have P0 over 1 plus M, PE 0 dot UZ. So at a price of P0, we have an unemployment rate of U0, and that gives me a certain level of output of Y0. They're negatively related. When unemployment goes up, output goes down. Output in this model is equal to the number of people working. Then we want to know, okay, so we say to ourselves, all right, what we know then is that at P0, we get Y0. What happens if we raise, we're going to ask this model a question now. All right, if we increase price in P1, we could decrease price too, it doesn't make any difference, just a little cleaner this way to talk about it. If we increase price to P1, what happens to output? So we're going to ask the question. If we increase price to P1, unemployment goes down, so output must go up. So at the higher price, P1, we get higher level of output, Y1. So the short run supply curve, the PE, fits. Looks like that. In fact, this has to be the natural rate, because if our expectations are correct, we're at the natural rate. If PE0 means PE equals P0, and I've been using that notation, that has to be the natural rate. And the other thing to recognize is what would happen if we were in the medium run. This is when expectations fixed. What if this changed 1-to-1 with prices? What would happen? So the supply curve is just P over 1 plus M equals PE F of U and Z. This is the supply curve. When this goes up, this has to go down. This is negatively related. So if P goes up, U has to go down to make these equal again. Right? But what if PE and P are equal? What's going to happen to those two terms? They're going to cancel. So you'll get, in the medium run only, you'll get 1 over 1 plus M is F of U and Z, which would give you a U, right? That would give you a value of U. But how is it related to P? Doesn't matter what P is, right? So that's this vertical line. So the medium run supply curve, where expectations are correct, is a vertical line. Because it doesn't matter what price is. You get the same output, the same unemployment, no matter what the price is. It doesn't change the value of the equilibrium at all. Over here, what happens is this curve shifts to perfectly offset. So you don't change the initial equilibrium at all. This goes to P1, D, F, W, and Z, and you don't get any change in unemployment at all. in that particular case. So that's the vertical supply curve we have the short run. And this is the equation we turned into the Phillips curve. This was 1 minus alpha z plus u. And we approximated that, and that was the Phillips curve. It's the same thing. In the long run, the Phillips curve is vertical because those curves cancel out. The median. So let's take a break and then see if you have more questions or about the lecture. So what I'll do, I'll get lots of email, I'll just tell people that, it's been 2 years. I'll fill it up for people who have the prerequisites, if there's seats left.
여기서 나가면 안 될 수도 있을 것 같아요. 여태까지 그런 거 한 번도 없었는데. 이렇게 빡쳐서 잘
Very, very good.
头的一个吃掉了，我以为是卡的，这个它没掉进去，卡在这个系统。原条两个，它是个推理，不管它是
완전 세.
结果呢？灯是那个甩的。
一码都没写。계속 하고 있어. 뭐라고 싶었어?
Well, there you go. Yes. You know how an increase in the price of oil affects the model, the aggregate supply curve in this case. The thing to realize is that we're going to model this in a somewhat peculiar way, but it works. It's a shortcut for modeling. So we've got a one-factor model, meaning that our production function, just what we had just now was two factors, capital and labor. But up before that chapter 10, we're using a one-factor model. Y equals N essentially. A is 1. Because we're holding technology constant. So if there's actually more factors than that, how can we model it? So suppose that we've got this certain markup on our labor, and that gives us a certain level of profit. If the price of oil goes up, we're going to need a bigger markup on labor to cover our costs. So we can model an increase in the price of oil as a change in the value of M, increase in the value of M. To cover the higher oil costs, we're going to have to mark up our labor even more. So we just take the model that we derived, the aggregate supply curve from P0 over 1 plus M0, PE0, F of U and Z. And that gave us this medium run supply curve and a short run supply curve for PE equals 0. So this is P0, and that's what I mean by that. So this U0 gives us a Y0. So whenever you want to know how a curve shifts, what you do is you hold either output constant and see how price changes, or hold price constant and see how output changes. So you can do it either way. What we're going to do here is just hold price constant and see how output changes. Now it's important to realize that this is actually the natural rate. When these two things intersect, and when the price is right, when the expectation is right, you're at the natural rate. So we're starting off here at the natural rate of output. We're going to increase M to P0 over 1 plus M1. That's going to cause this line to shift down. So we're going to get a higher unemployment rate. Now, one question we want to know is, did that just shift the short run, or did it shift both of these curves? Well, notice that our expectations are still correct. P0 hasn't changed. PE0 hasn't changed. It was correct before, it's correct now. So what we have is a new natural rate. That is, this whole curve shifts. So what's going to happen is that both of these curves are going to shift because unemployment is higher, output is lower. So both of these curves are going to shift horizontally. It's still PE equals P0. It just shifted over that way. So you have a new natural rate, a short run supply curve. Expectation is so correct when we're at the long run supply curve. The whole, both curves just shift to the left with an increase in the price of oil. See, when you change just expectations, that breaks the link between P0. If I hold those constant, then I'm not shifting the long run supply curve because now PE and P aren't the same anymore. So when I just shift expectations, it just shifts the short run. When I change M, that changes the natural rate. Okay.
So if you increase the price of it,
Yes, that's what moves along shortly. We increase P with PE constant, then we're breaking the link that they're equal, so we're not on the long run supply curve. Then we're moving along the short run. But in this case, we haven't changed either one, so we must be on the long run. And this is a shift in the long run because we're still at PE equals P0. If you change PE, this thing, with P constant, this thing shifts. You change P with PE constant, move along. That's how you derive the short run supply curve. You change P around, only P constant. So then we can also do things like said, how does that work on an aggregate demand, aggregate supply diagram? So we start with medium run supply, short run supply, P equals P0. That's P0. Okay, 0. price of oil goes up, you shift both curves. Yes. Right there. Goes oil. And you'd end up at that point. When the short run supply curve is where it hits the demand curve. So that means your new short run equilibrium right there. See that? Then, because this is the new natural rate, the economy is overheated. You're actually above the new natural rate. Below the old one, you're above the new one. So over time, the supply curve would start shifting. Until you have a new short run supply, PE equals P1, where this value equals P1. So when you have the demand curve and work out the full equilibrium effects, there's more to it. But just doing the shift is this. So you go from A to B in the short run, and then from B to C in the medium run. So A to B is the short run, and B to C gets you back to the medium run. And so you'd expect to see a stagflationary episode, wouldn't you? What would you see in this transition in the data? You'd see falling output, rising unemployment. The natural rate is higher. Unemployment's going to begin drifting up. You're going to see prices drifting up. So you're going to see stagflation. You're going to see inflation going up and unemployment going up at the same time. So oil price shocks tend to impose stagflationary effects. Now, the mistake they made in the 60s is, or the 70s, is they kept shooting at this target. So if you're the Fed and you think this is the right target, what would you do next? You'd try to hit that point, right? You'd increase the aggregate demand curve. Then what would happen? You'd have an overheated economy, and the supply curve would go back even more, and you get even more inflation. That's basically what happened in the 70s. They kept trying to hit this higher output target, this lower unemployment. They didn't realize the natural rate had gone up. They shot for the old 4% unemployment target. And as they kept pushing demand up, the supply kept pushing back. And you got this general rise in prices and high unemployment rates at the same time. So you can see how the application of demand-side tools would say, you know, if this is a demand-side recession, it's easy. You just bring demand back where it started. The application of these demand-side tools to a supply shock didn't work out very well. And that's one of the mistakes they made in the 70s. So the model explains fairly easily exactly what we see in the data in the 1970s. and other periods. On to growth. All right. So this is not on the test. Looks like you ran out of questions. Too early to quit. So here we go. So we're trying to understand economic growth. What makes countries grow? We're trying to understand the rapid rates of growth we've seen over time in developing countries, places like China, even developing countries. What's responsible for that rapid rate of growth? What does our model tell us? And the other fact that we saw from our growth model, growth rates tending to converge over time. It's looking like income, standards of living is a better way to say it. The standards of living seem to be converging over time. We saw that in the data. We looked at the last 60 years. We started off with quite diverse standards of living of a variety of countries, and they become closer and closer together over time. So it looks like countries that are behind more grow faster. Otherwise, they couldn't catch up. Why is that? What's going on there? How can you explain that in the data? And so on. So we really want to build a growth model. And the key tool we're going to use is a production function. And we talked about this already today. Y is a function of capital and labor, and we're going to assume constant returns to scale. So that we can write Y over N is some function of K over N in 1, and that's clumsy. So we're just going to write F of K over N in 1 as F of K over N. There's no reason to keep writing that 1. So we're going to write our production function in that way. So we can actually graph this thing. So our model is Y is some function of K over N. So when we graph that production function, we're going to graph it like this. It'll just be so this is K over N, and this is Y over N. So that's a graph of the relationship between the standard of living and capital per worker. Now, what this is showing us is that for an individual, if we double both K and N, we double output. This should be Y over N, sorry. If we double K and N, we double Y. That's what constant returns to scale means. But for an individual factor, if we just double capital, we less than double output, and the amount of the output goes up, gets smaller and smaller and smaller. We have diminishing returns. We keep increasing capital, labor constant, we get diminishing returns. So what this is showing us is that you get less and less output per person as you increase K over N. When it's relatively steep, a 1 chalk unit increase, where is that? Gives me that much of an increase in the standard of living. Out here, the same increase gives me a much smaller change in output. So the same increase in K over N gives us less and less increase in the standard of living. So there's diminishing returns in K over N in this case. The way we can graph an increase in technology is a rotation in the curve. So here's F prime. That's an increase in technology. What it tells us is for the same amount of capital and labor, instead of getting that Y over N, we'll get an even bigger Y over N. So an increase in technology increases output, increases the standard of living for a given K. So this tells us something important, actually. We cannot, according to this model, you can't sustain growth through capital accumulation. Because as K over N gets bigger and bigger and bigger, what's going to happen to the standard of living eventually? It's going to converge to a fixed, you're not going to get any increase in Y over N. In the limit, this thing will get completely flat. And so increases in K over N, capital accumulation, will not sustain growth. You can grow for a while by just increasing capital, but those growth rates will come smaller and smaller and smaller and smaller. You just keep adding the same amount of capital. So if you want to sustain growth over time, you need to have technological progress that makes this thing steeper and steeper. And that technological progress combined with capital accumulation can sustain growth through time. And so technological progress is the key to sustaining long-run growth. Capital accumulation alone is not going to do it. Okay. So here, let's start building a model. So far we've assumed, a production function, y over n, y is f of k over n. We've assumed constant returns to scale, so we can write y over n is f of k over n. Now we're going to make a couple more assumptions to make our lives easy. What we want to do is fix n in this model and just look at how capital and y over n are related. So we want to look at the relationship between k and y, essentially, and then relate that to savings. So we want to fix n. So we're going to make some additional assumptions. So we'll also assume that the size of the population participation rate, and the unemployment rate are all constant. That gives us a fixed n. Remember, the labor force is the participation rate, the labor force participation rate times the population. And then n, the number of workers, is the labor force times 1 minus the unemployment rate. So we're trying to fix n to make our life simple. If either of these change, we're going to change the labor force. If the labor force changes, n will change. So we'll hold both of those constant. If the unemployment rate changes, we'll change n. So we'll hold that constant. So making those three assumptions just gives us a fixed n. And that'll make things simple. Under that assumption, output per worker, output per person, and output all move in proportion. So we can talk about, I'll probably just talk about output, we can talk about any one of these. Those are all just going to move in proportion. Because these are all fixed. So they'll just move in proportion. The final assumption we're going to make is that there's no technological progress. We'll relax that in the next chapter, but for now it's easiest to start very simply. So we're just trying to see how k and y are related. So we can write yt over n as some function of kt over n. So k and y can vary over time, n is fixed under our assumption. So this gives us one relationship between output and capital accumulation. We're going to write another one now, and then we're going to put them together in a graph. So, let's remember that I is savings plus T minus G. We want to focus on private savings. So we'll set T equal to G to make it simpler. We could set that equal to a constant. As long as it's a constant, I only want private sector savings to vary. If we're going to make it a constant, it's easiest to just make it 0. So we're just going to focus on private saving. T minus G is public or forced savings. We're not going to have any of that initially. So I equals S. We're going to assume that savings is proportional to output. So savings is just some function of output, some fraction of output in the model. Then we need to know how capital changes over time. So now let's look at capital accumulation, and then we'll bring these two things into it. So we're going to just write down what should be obvious when you think about it. So this is invested. And this is the depreciation rate. So you start with some capital at time t, and say this is 5%. 5% of it depreciates. So 95% of it's left over and goes into the next period. So 1 minus the depreciation rate is a capital that survives. Depreciation rate times capital is the stuff that's destroyed through just the normal depreciation. And this is the change, this is what you add to the capital stock. Right?
Is that a year as 1 minus?
That's delta. It's ready to do it. It's this is cap delta. That's the lowercase. That's the one we learned. This is the lowercase version. So it's a common symbol for depreciation. IT equals ST equals SYT. YT. So we'll get to there in a minute. So first, we can say then that KT plus 1 is 1 minus delta KT plus SYT. Because investment equals savings equals SYT. Right? So it must be that K T plus 1 over N equals 1 minus delta times KT over N plus S times YT over N. And we know that that's F of KT over N. I'm not going to use that, but this is how capital per person evolves through time. this is a description of how capital changes through time. There's investment, and there's depreciation. Now, it's convenient to write this as kt plus 1 over n minus kt over n. So I'm just going to take 1 times this and move to the other side, is syt over n minus delta kt over n. So we have that the change in capital per person is SF of KT over N minus delta KT over N. So this side is the change in K over N from T to T plus 1. And what's that going to depend upon? If you're investing more than you're depreciating, capital is going up. Change is positive. If you're investing less than you're depreciating, capital would be falling. So this is just investment at T, and this is just depreciation at T. So whether capital is rising or falling depends upon whether or not depreciation is bigger or smaller than investment. Someone drops a bunch of bombs on you, that's like having a great big depreciation rate, right? Your capital's just evaporating before your eyes. So you get a great big depreciation rate because you're getting bombed, and just an average investment, your capital in your country is probably going down. And you can use this because it's just that simple. So we want to find the steady state. I want to find the point where capital is neither rising nor falling. And that's called the steady state. I want to find the point. Let's find the point graphically where delta K over N is equal to 0. That's called the steady state. It's where nothing would be changing. So that has to be where these two things are equal, right? It has to be where these are equal. Where this equals this is the steady state. So I'm going to graph this and graph this. Where they cross is the steady state. That's where you wouldn't have any growth at all. You'd be stationary, static. So we can graph, let's put K over N on this axis, KT over N. And let's first graph the production function. So this is F of KT over N. That's just this production function. This line here is a fraction of it. So SKT over N must look exactly the same. It's just rotated down. So this is SF of KT over N. It looks just like the production function but it's a fraction of it. Like S is 1/2. Well, I haven't dropped right for 1/2. If it was 1/2, it'd be halfway between, everywhere. So it looks exactly the same, it's just rotated down by the fraction S. This is just a straight line from the origin, right? The graph of this line, forget the minus sign, I want to know whether these are equal. This is 0, where S of f of t equals this. So this other term is just a straight line from the origin. So this is delta kt over n. So where those two things are equal, SF equals delta k, where this equals this, that's that point. That has to be where k over n is stationary. That's the steady state. That's where this is 0. Where capital K over n is growing or falling. And at the steady state, we would have that amount of output. So that would be the steady state. So once you get to this point, you just stop growing. And you end up with a stationary standard of living. See that? Now we can ask what happens in a minute to the steady state standard of living as S changes, as the savings rate changes. And clearly if S goes up, your standard of living is going to rise. And so that the steady state standard of living, the level of it, will depend critically on the savings rate. But a higher savings rate does not give you a permanently higher growth rate. And I'm getting ahead of myself. Okay, let's do one more thing here. Let's suppose we're below the steady state. So let's draw the same thing here, these 3 lines. This is delta kt over n. This is the production function. And this is S f of kt over n. And let's start at this kt over n, right here. And I'm going to put this as C and this at D. So at that kt over n, call it 0. It must be that delta k over n, that's point C. At this k over n, that's delta k over n. That's point C, right? That is less than that point, which is S f of kt over n. See that? So if investment is bigger than depreciation, what must be happening to the capital stock? K over n. Remember that k t plus 1 over n minus kt over n is S f of kt over n minus delta kt over n. So if this is bigger than this, what's happening to the capital stock? It's increasing. K over n is going up. So we'll move in that direction until we hit what? The steady state. And so this model says we'll grow over time until we hit the steady state. If we were on this side, we'd move in that direction. So this is an attractor. This is an equilibrium point. This is where we'll end up in the long run of this model. And so if you start below the steady state, you'll see growth for a while, but growth will eventually peter out. And you'll end up with a fixed standard of living and a fixed amount of capital per person. So we're not getting permanent growth out of this model yet. We get stuck at a steady state. So you have, in the long run, that standard of living, because that's why they're in. I guess I could call these SS too. It's typically we call those indexes of SS, so you know it's a steady state. Let me do one more thing, and then I'll get you out of here. What does this model predict will happen if there's an increase in the savings rate? Let's start at a steady state. It's delta K over N. Production function. S0, F of K over N. So we start off at that steady state with that level of standard of living. Then what happens if the saving rate goes up? This curve will change, and this will rotate up. So you'll get a rotation upward in this line to S1 F K over N. You'll get a higher standard of living. So an increase in the savings rate will cause you to grow for a while, but not forever. You'll eventually hit a new steady state. So you'd see, if you were just tracking y over n over time, here's y over n. Saving rate goes up, it would rise up to a new level, and then it would level off again. And so you get growth for a while with higher savings, but it doesn't generate a permanently higher standard of living like we've seen over the last 200 years or so. So something's missing from the model that will explain why we had permanent growth instead of getting stuck in some stationary state. Yeah?
So you could increase investment, but you won't increase outlay if you do that.
Temporarily you will. But you'll temporarily you will, but you'll get stuck in a new steady state. You start out at y over n0, and you go up to y over n1. And the higher savings is higher investment. But you won't this won't grow permanently, no. That's the point. Our standard of living seems to rise continuously over time. That's not happening in this model. So we must be missing something important. And it's technological progress. That's what we need to have. So, questions about this? No. If I ask a question, there was an 8. So we'll finish. We'll stop right there. We're 2 minutes to go. Sorry.